So in exercise 2111, we're continuing our multi-step syntheses with carboxylic acids and their derivatives. So if we look at these two molecules, we have benzene in both of them. The difference is what's coming off of it. And the reactants, we have a leaving group, which leaves. It's no longer in the product. And in its place, we have a carbon with an OH on it. So the first thing we have to do is make this new carbon-to-carbon bond. Now, really, normally, if you just had benzene, the way you would make a carbon-to-carbon bond is with a Friedel-Crafts reaction. But because we have a bromine on it already, we could turn it into a Grignard. So if we just plop some solid magnesium there, the magnesium will insert itself in between the bromine and the carbon, and you'll get the magnesium bromide. And so because the bromine is already there, and because the bromine is what we want to replace, it ends up being more efficient to do this, to use the Grignard reagent. Because now we have this carbon nucleophile. What this is effectively is a positive charge on the magnesium and a negative charge on that carbon. So that's our nucleophile. And if we just want to add one carbon on here as an electrophile, you could potentially, use something like methyl iodide. So that's one option. Another option, though, we're sort of mapping out our thoughts, you could say do methyl iodide. You have your leaving group, and you'd replace that with your nucleophile in an SN2 reaction. So you could imagine having something like that. It gives you toluene. Or maybe an even more clever way, because it gets us closer to having that functional group, is to use carbon dioxide as your carbon electrophile. Because then as this attacks that carbon, you end up with a carboxylate. So the benzene ring with the two O's, one of them has a negative charge. So you'd have to stabilize that negative charge here. We'll worry about this. We'll come back to that in a second. Right now, let's continue with this carboxylate. If we treated that with H3O+, just to stabilize that charge, we'd have benzoic acid. And if we want to get from benzoic acid to this alcohol, we notice that what we have are fewer bonds to oxygen. Here we have 3, here we only have 1. So we want to do the opposite of an oxidation. We would want to do a reduction. So we could use a strong reducing agent, like lithium aluminum hydride, and follow that up with a water wash to do the proton transfer that takes the negative charge away from an oxygen. So that would turn that into the alcohol that we want. So that's one possible route. You could do this, make a Grignard reagent, have the reactive Grignard reagent with the carboxylic acid, treat that with just a proton, and then reduce it to an alcohol. If we did use methyl iodide and got this toluene, there are a couple things we can do. You could oxidize it. You could use a strong oxidizing agent, Na2Cr2O7, with an acid water wash. And that would turn that into benzoic acid, like we saw in the previous video. So long as you have a hydrogen on the benzylic position, a strong oxidizing agent can oxidize that position straight to a carboxylic acid and kick everything else there off. And then we can reduce it just like in the previous example. So lithium aluminum hydride followed by water, and that would just replace the 2 bonds to that oxygen with 2 bonds to hydrogens. So these 2 bonds with 2 bonds to implied hydrogens there. So that's another option. You could create the Grignard reagent, treat it with methyl iodide, oxidize the benzylic position, and then reduce it. Or another one. So the possibilities are very exciting. You have this benzylic position. You could treat that with you could do a radical reaction. Treat it with N-bromosuccinimide and light, and that will put a bromine on that benzylic position. And then this is a leaving group. You can just treat it with an OH nucleophile. So something like NaOH. And that would give you your product. So in all three of these cases, and you may even be able to think of more, in all three of these cases we end up with the same thing. The thing we want, the recipe you would use, and here I'll list these recipes out separately, but the recipe you would use would depend on your circumstances. What do you have in your laboratory in terms of equipment or chemicals? How much money do you have to work with? How much time do you have? What efficiency, what different efficiency would you get in each of these? So you'd use those things to think about them. So let's see, we came up I think with 3 different recipes. Let's say the first recipe was adding magnesium. So here we're going to follow this one. First recipe was magnesium, and then we'll treat that with carbon dioxide, followed by an acid wash. And then we had the carboxylic acid, the benzoic acid, that we reduced using lithium aluminum hydride, followed by water. So that's one possibility. Another possibility is the second one that we came up with. So you could again make the Grignard reagent, treat it with magnesium, follow that up, follow that up with methyl iodide, or it could be methyl bromide, methyl chloride, just something to do an SN2 reaction with. Then you have toluene, which you can oxidize to benzoic acid using sodium dichromate in an acid water wash. And once you have that carboxylic acid, you can reduce it with the lithium aluminum hydride, followed by water. And then last, we saw that you can sort of do this radical reaction in an extra SN2. So in that case, we created the Grignard reagent, treated it with methyl iodide. Then we did a radical reaction with NBS and light to put the bromine on the benzylic position. And then we did an SN2 reaction with sodium hydroxide. So those are all possible solutions to making this transformation happen. Okay, then we have B. Now with B, this is sort of something we already did in this last one. So in this last one, it's the same thing, but now we're starting at the toluene. So we really have these 2 options for B. So it's sort of the same solution. But if we look at it with sort of fresh eyes, you can see you have a toluene here. You can look at this either as a substitution possibility, where you're trying to replace something here with an OH, or you can look at it as an oxidation exercise, where you have no bonds to oxygen, you have 1 bond to oxygen. I think the oxidation one would be a little clearer to see at first, so let's do that one first. We'll do the other one too. So with the oxidation one, we have no bonds to oxygen here. If we want to create more bonds, unfortunately the benzylic position is really reactive, so the only way to make it react is to have it go straight to the carboxylic acid. So we might as well use sodium dichromate in water and sulfuric acid. And that gives us benzoic acid. And then if you compare this with the product that we want, you'll notice this one has more bonds to oxygen than we want. So now we have too many bonds to oxygen. To reduce the bonds to oxygen, you do a reduction. You use a strong reducing agent like lithium aluminum hydride. And you always follow that up with water. So if you think of this in terms of oxidation and reduction, one possibility is just doing using a strong oxidizing agent. followed by a strong reducing agent, and then a water wash. So that's one possibility. Another possibility is to think of this as a substitution. If only we could get a leaving group here, we could use an OH nucleophile to replace it, do an SN2 reaction. And we can get a leaving group there. It's the benzylic position, so we would just have to use N-bromosuccinimide and light, and that will put a bromine there. And then use NaOH. The OH minus will swoop in as a nucleophile. Kick the leaving group off, and you'll have your product. So that's another possibility. Now you would only ever have to list one of these on a test. You wouldn't have to list every possibility. Who knows? There are even more. There are probably even more reactions that could make this transformation happen. So long as you know one way of getting from the reactant to the product, you'd be completely fine. But you can see what an opportunity for creativity there is here, and how fun these problems are, because they're not really linear necessarily. They require a little bit of thought, a little bit of chess playing, seeing into the future as you're planning for the present. And there are